So for problem 3 in the homework, it says the figure below shows a monochromatic beam of light striking the right-hand face of a right-angle prism at a normal incidence, meaning that the wavelength is irrelevant and it enters flat at a 90-degree angle right over here this way. If theta t is 25.7, what is the index of refraction of the prism, assuming that alpha is some angle? So we need to take note of what we're given here. First of all, we can redraw this diagram for our convenience because looking at it sideways is not going to help anyone. If we're looking at our prism, we'll see that some ray of light, let's make it yellow for convenience, right? No, that's not correct. Some ray of light enters at a 90-degree angle and it exits at an angle that is no longer 90 degrees. We can make it arbitrarily large because if we work in generality, we can fix it later. So we also should keep in mind the true normal of the entering ray of light. And you'll notice right away that if we recall Snell's law, it references both angles relative to the normal of the surface. But there's two normals here. There's the normal of the surface where we enter, and then there's the normal of the triangle. So we additionally need to consider this normal. Now, it's not going to be drawn perfectly. I'll just draw it a little bit iteratively. That looks normal enough to me. So if you see, we now have two different normals, and we need to ask, which do we consider this problem from? If you notice, when it enters the prism, it continues going straight. So we can assume that there's no diffraction occurring at this point. So we instead change our focus down over here where it's angled, and we say that this is our new area for Snell's law. So what we have to do first is we have to figure out what angles are actually given and what can we work with, right? So for starters, we know that this is given, right? This is 90 degrees. We know that this is given. This is alpha. And now we also know that this is given. Right here, this angle is theta t. Now again, to apply Snell's law, we need the angle relative to the normal. So doing a little bit of thinking, we have found that the angle that we actually need is not this black one right here, but this green angle right here. We'll call it theta green, right? I'll omit the G for green. So we have to ask, how do we get theta green? Well, we know theta t, and we know that theta green has to be a sum of whatever this angle is and whatever this angle is, right? Let's mark this angle in red. And if you'll remember from geometry, these two lines intersect, therefore these angles are the same, right? What else do we know about this triangle? We know this is a perpendicular intersection, so we know that this angle is 90. Therefore, we know that this red angle is 90 minus this angle over here, this pink angle, right? So how would we get this pink angle? Well, what else do we know? We created this perpendicular intersection right over here, so we know its angle is perpendicular to the prism. So we can draw that, and additionally we can draw an internal perpendicular angle, right? What else do we know? We know that if this is 90, and if this is given angle alpha, we know the third angle of our triangle, since the sum of the angles in a triangle has to be 180 degrees, and given two of them we can find a third. So let this one be beta, and we know that the angle of beta is equal to 90 minus alpha, right? So now that we have one angle here, and we have a second angle of a triangle, we can repeat the step, right? We have two, we can find the third, but notice, in this triangle, we have 90 alpha, and that gives us beta. However, in this triangle, we have 90 and beta. So logically, this pink angle right here is actually alpha. Maybe a little small. Let's draw this like here and give a little arrow. Okay, now we have a third triangle. What's in this third triangle? We have 90, alpha, and an unknown angle. And if we look at our main triangle, it's 90 degrees, it's alpha, and our third angle is beta. So this allows us to conclude that this red angle itself is also beta. All right, that's a little small, so let me draw it outside here. That's right here, and consequently right here. So now that we have our red angle and we're given our black angle, we know that our green angle, let's call it theta, theta green, right, is going to be equal to our given theta t plus our beta. And we know what beta is, it's 90 minus alpha. So now the consideration to make is, how do we apply Snell's law? Snell's law tells us that given a surface where the index of refraction between the two mediums, let's give this n1 and n2, is different, right? Because if it's not different, it's just continuing through the same medium. The light will bend in a manner, that's supposed to be a straight line. The light will bend in a manner that's proportional to these indices of refraction, right? Let's make them yellow so they're easier to see. So if we have an angle over here, let's call this theta 1, and we have an angle over here, let's call this theta 2, Snell's law tells us that if we take the product of n1 and sine of this first angle, it is going to be equal to the second index of refraction times, once again, the sine of our second angle. Now we have to consider where in our image can we apply Snell's law. Once again, we only have 2 points where the light enters and exits, right? Over here, we can see that it enters perpendicular to the flat side of the prism, but this doesn't help us very much because there is no diffraction. This would be a pointless analysis. So instead, we have to focus on this area right here in purple. So for convenience, I'm going to copy this over. So what is this telling us? Well, we can see what our normal is right here. It's this blue line. And just for clarity, let me highlight the blue line in pink. We see that our ray of light is still in yellow, so we can conclude that our two angles, let's leave this as pink, we can conclude that the two angles that we're working with are beta in red, and right over here in green is the theta we just found. So once again, we apply Snell's law. Sine of beta is going to be equal to n2 times the sine of, let's call it, our green angle. Okay. The only thing left to determine is what our two indices of refraction are. Notice that when we're going into the prism, we're coming in supposedly from air. The problem doesn't mention this, but this is an assumption we're allowed to make because there's no water, otherwise it would tell us. There's no other surface, otherwise it would tell us. So we assume it's from air, and as a matter of definition, air has an index of refraction of 1, right? So let's consider which side of our Snell's law application right over here, which side of this is air and which side is the prism. Obviously, the side with beta is the prism, so we're going to rename this not to n1 but to np for n prism. And we're going to say that n2 is actually n of air, and we know that's equal to 1. So when we algebraically rearrange, we can say that n of the prism is going to be equal to sine, I'm going to copy again, sine of the green angle, over, and I'm going to copy again, sine of the red angle. The red angle is beta, and we know that our green angle is once again beta plus our given angle theta t. So the last thing to consider is this in degrees or in radians? Well, quite obviously, it's in degrees. You're given it in terms of degrees, so it's in degrees. So now the only thing left to do is to check if this works. So we can switch over to Desmos, and you can see our red angle is going to be beta, which is 90 minus our alpha, and our green angle is going to be our given theta t plus our red angle as defined. The index of refraction of our prism is going to be the sine of the green angle over the sine of the red angle. And if we input our theta and alpha, if we look back at our problem, theta is given as 25.7 and alpha is given as 59.4. So it's giving us an answer of 1.6343. Now we can go back, if I find my mouse. Now we can go back to the WebAssign and check if our answer is correct. And we can see that the answer is indeed correct. Okay, that's it for this one. This problem wasn't too complicated on the calculations, but you needed to be able to recognize which angles are similar and where Snell's law actually applies. And this is important for the actual other two problems, 1 and 2, because you can easily make the mistake of not recognizing which angle to consider for Snell's law. So whenever you're doing a Snell's law problem, always draw out the diagram, recognize what surfaces you're going between, and recognize the angles, because sometimes the problems will happily give you an angle right over here. That's incorrect. Will give you an angle right over here and mention it in words, but not tell you to change it in your calculation. Likewise, they can give you an angle right here and one angle right here, and you'll have to figure it out yourself. So always pay attention, and when in doubt, you can draw a diagram.